The second part of section 1.2 deals with stretches. Whenever any object is stretched, the shape of the result and the original are not congruent. That means the original and the new transformed shape are not the same size. They are not necessarily the same shape. When functions are stretched about the x and y axis, their shapes change. So just like we reflected about the x and y axis in the previous part, we are going to stretch about the x and y axis in this section. So we're going to start with the question, what happens when we multiply a function by a coefficient? In other words, what happens if we take parameter a and put it in front of f at x? We've already talked about what happens when a is negative. We know that the result is a reflection. But what happens if a is a number, if a is a coefficient? We're going to explore that by looking at these three graphs below. So we are going to look at the first bullet. Using the graph of the function, f at x equals 4 minus x squared, which is this solid graph here, state the domain and range using interval notation. Okay, we can do that. So let's have a look at this solid graph. I can see that the lowest x value is negative infinity because it's getting wider and wider and wider to forever in a negative direction. It's also doing that in a positive direction. So in interval notation, we are going to write that domain as open bracket, negative infinity, comma, positive infinity, open bracket. The range, on the other hand, is limited. Our highest y value here is positive 4, but because this opens down, it's going to continue down, down, down forever. So our lowest y value is negative infinity. So our range is from negative infinity to positive 4. Because 4 is included in the range, we're going to use a closed bracket around it. Okay, let's compare two graphs. We're going to compare f at x, which is this black graph in the middle, with g at x. Now, let's look at the equation of g at x. G at x is the exact same equation as f at x, except there is a coefficient of 2 in front. So our parameter a is 2. Let's look up here and look at what that graph looks like. Here is g at x. G at x is this blue dotted graph right here. It is the result of putting the coefficient of 2 in front of f at x. How would we describe g at x as a transformation of f at x? Well, here's what I notice. I notice that it is taller than f at x. Okay, if we even have a look at the y-intercept, f at x is intercepting the y-axis at 4, whereas g at x is doing that at 8. Okay, it's a little skinnier, but it's really taller. What it looks like is we held down the x-axis, we took f at x and pulled it up this way, up above the x-axis. So we held on to the x-axis, and it's like we took it and we pulled it up this way, and then we took these parts here and pulled them down this way. But we held on to that x-axis. So a way to put that in words is to say this. g at x, I'll maybe write it in blue since g at x is our blue function. G at x is a vertical stretch about the x-axis. And let's be specific about how much we stretched it. We noticed that the y-intercept went from 4 to 8. We also noticed that the coefficient that we put in front is a 2. So I'm going to say that was stretched by a factor of 2. That was my coefficient. And we can clearly see that g at x is twice as tall as f at x. Next, let's compare f at x to h at x. Let's look at what h at x looks like. H at x, again, the equation looks very similar to f at x. It has that 4 minus x squared, just like f at x has, but h at x has its own coefficient. It has a coefficient of 1/2 in front. So we can tell that there is going to be a transformation here because the equation has been transformed. Let's have a look at the graph and see what that transformation is. Well, when I compare the two, I notice that h at x is shorter than f at x. This y-intercept is 4, whereas this y-intercept is 2. So it's almost like I pulled that down. At the same time, notice that it's almost like we took our y, or underneath our x-axis, it's kind of like we took them and pulled them up, kind of made them this way. So we are pulling towards that y or x-axis. So the way that we would describe that change would be to say that h at x is a vertical stretch again. We can see that action is vertical. So h at x is a vertical stretch. Again, it's a vertical stretch about the x-axis. But notice that in this case, our stretch factor is not 2. Our stretch factor in this case is 1/2. How do we know that? Well, our coefficient is 1/2, and we recognize that it looks like h at x is half as tall as g at x, or of f at x. So our conclusion then, when we put that coefficient in front, we are going to have a vertical stretch. If we start with y equals f at x, and either we replace y with y over a, or we put that coefficient in front, we write y equals a times f at x. What ends up happening is the result is a vertical stretch about the x-axis by a factor of a. So whatever that a value is, whatever that coefficient is, that's what we are stretching it by. Now, what are we really doing here? Well, we compared up here, we compared our y-intercepts. So notice that the x values are staying the same. It's the y values that are changing. Okay, it's getting taller. It's getting shorter. It's the y values that are changing. So when we're going to talk about mapping, we're going to talk about a change to the y value, not a change to the x value. So how is that y value changing? Well, it's changing by a factor of a. So our mapping is going to be this. Our old point, xy, is going to become, x stays the same, but y is going to change. It's going to change by a factor of a. Now we need to be careful. We just finished talking about reflections, and we talked about, well, what happens when a is negative? In this case, we're going to look at a as being a number. So what we're going to do is we're going to say the absolute value of a, because if there happens to be an a value that's negative, whenever we talk about the stretch factor, we want to talk about it using a positive value. So we will use the absolute value of a. Okay, on the other hand, what happens when we multiply the x coordinate by a coefficient? So instead of talking about parameter a, which is in front of the function, we're going to talk about parameter b, which is inside the function, right next to the x. So let's have a look at these three graphs that are drawn for us. Let's start with our basic function f at x, which again is this black graph in the middle. The equation of f at x is root x plus 4. So there's our guy. We're going to transform him in a second. The first thing we want to do is state the domain and range in set builder notation. So we can notice that our lowest x value here is at -4. And then the graph extends out to positive infinity from there. So we are going to say the domain is the set of all x such that x is greater than or equal to -4. Otherwise, x is an element of the reals. Our range, our lowest y value is 0. And again, it extends up from there. So it's going to keep continuing up to positive infinity. So our range is going to be the set of all y such that y is greater than or equal to 0. Otherwise, y is an element of the reals. Okay, so let's compare these two graphs, f at x and g at x. F at x right here, okay, is going to be that black graph. Now let's look at g at x. The equation of g at x looks different than the equation of f at x. F at x is root x plus 4, and g at x is root 2x plus 4. So we can see a difference there. Where's the difference? Right in front of the x. That tells us that we are going to have some sort of stretch. Let's look at what that stretch is. Looks like here, where it used to cross the x-axis at -4, it's almost like it's been pulled in horizontally to cross at -2. Same thing here. It looks like everything on this side of that y-axis has been pulled in horizontally towards that axis. It's all kind of being pulled in. So if I was to describe this g at x as a transformation of f at x, I would say that it is a horizontal stretch. Now it's being horizontally stretched about the y-axis, and it's being stretched by a specific amount. Now we need to be careful. The coefficient that we're putting in here is a 2, but have a look at this stretch. When we pull, especially we can see it here, it is now half the distance away from that y-axis. It used to be 4 units away. Now it's only 2 units away. Same thing here. These are being pulled in to the left. So it's a horizontal stretch about the y-axis, but our stretch factor is not 2. It's by a stretch factor of 1/2. It's getting pulled in closer, half the distance from that y-axis, which is kind of weird because that did not happen when we were talking about stretching about the x-axis. The A value was our stretch factor. In this case, our B value is not necessarily our stretch factor. Let's have a look at h at x. Oh, sorry, let's compare the domains. So the domain of this one is going to be, well, the lowest x value is -2. It also opens up and to the right, so it continues to infinity. So the domain of this one is going to be the set of all x, such that x is greater than or equal to -2. Otherwise, x is an element of the reals. Now let's have a look at h at x. Let's look first at the equation of h at x. So I notice that for the equation of h at x, it's 1/2 x plus 4. So f at x was just x plus 4, h at x 1/2 x plus 4. That coefficient was put in front of the x, and the coefficient that we are using is 1/2. Let's look at the results. So looking at the black graph and at the red graph, it looks like this point here has been stretched out this way. So it used to be 4 units away from the y-axis. Now it is 8 units away from the y-axis. Same thing, it looks like these points out here have been stretched out in that direction. So they're being pulled outwards. And notice by how much. So we used to have an x-intercept of -4. Now it's pulled out to -8. So if we were to describe this transformation, we would say again that h at x is a horizontal stretch. We can see that that action is horizontal. We can see it's being stretched about the y-axis. Now, our stretch factor is not 1/2. In this case, we have a stretch factor of 2. And we can see that again, even just looking at that left-hand side, it's definitely being pulled out, it's being stretched by a factor 2. It's twice as far from the y-axis as it was before. Now, we should notice a pattern there. When our coefficient was 2, our stretch factor is 1/2. When our stretch factor was when our coefficient was 1/2, our stretch factor is 2. So we need to be very, very aware that when we are looking at a horizontal stretch, the stretch factor is the reciprocal of the B value. Let's compare our two domains here. So the domain of h at x is the set of all x such that x is greater than or equal to -8. Otherwise, x is an element of the reals. Based on that exploration, let's go ahead and make a conclusion. If f at x is replaced with f at bx, so if we are looking at that parameter b and we are putting a coefficient in front of the x part of that function, the result is a horizontal stretch about the y-axis by a factor of, we're not going to say b, we're going to say the reciprocal of b, 1 over b. And we're going to be even more specific. Sometimes b might be negative, which means that we have a reflection. But if we have a negative and a coefficient, our stretch factor is going to be the absolute value of b. We always want our stretch factor to be positive. Well, how do we make a horizontal stretch happen? Well, you'll notice that it's affecting only the x values. The y values are staying the same. We could have checked that if we had done the range here for all of these, they would be the same. But we can even see these y values, all the same in these graphs. The y values are unaffected. We are only looking at the x values. So our mapping is going to be old function xy, new coordinate 1 over b times x, y remains unchanged. Let's make a summary of all of that together. So here's a nice chart that we can fill in that helps us sort of get everything straight. If we start with the function y equals f at x and we stretch it about the x-axis, so that means that our x-axis is horizontal, but we are stretching about the x-axis. Our verbal description is that that is a vertical stretch. The mapping is xy becomes xay. Our function goes from being f at x to being y equals a times f at x. Now, location of invariant points. Will there be invariant points if we have a stretch? There will be. So let's go up and have a look at that vertical stretch up here. And you'll notice that some of the points have stayed exactly the same. The points that are exactly the same on all three of these, and you can see it in this one, it's that x-intercept. And that makes sense. If we're stretching about the x-axis, anything that's lying right on the x-axis is not going to get stretched. So if we have a vertical stretch, our x-intercepts are going to be invariant. Let's put that down. So location of invariant points, x-intercepts. And I'll put intercept or intercepts. We might have one, we might have more than one. If we start with a function y equals f at x and we stretch it about the y-axis, so this means we're going to hold down the y-axis and we are going to pull that function on either side of the y-axis. This is referred to as a horizontal stretch. That means that our y value stays the same. Our x value is going to change, and it changes by the reciprocal of the b value. So 1 over b times x. Our new function goes from being just y equals f at x to being y equals f at bx. And again, because we are stretching about the y-axis, anything that lies on the y-axis will not get stretched. So our invariant points, if we are doing just a horizontal stretch, will be the y-intercept. We will not have invariant points if we do a stretch in both directions. But if we do just a vertical stretch, x-intercepts will be invariant. If we do just a horizontal stretch, the y-intercept will be invariant. Okay, so we've done a good summary there of what we've talked about. Let's go ahead and practice some of this with examples. Example 1. Given the graph of y equals f at x, sketch the graphs of g at x, which is equal to 3 times f at x, and h at x, which is equal to f at 2x. We're going to state the domain, the range, and the number of invariant points for both transformations. Let's start with g at x. So g at x is equal to 3 times f at x. That coefficient is in front of the function. That means we are talking about parameter a. That means that g at x is representing a vertical stretch about the x-axis by a factor of 3. In other words, this is going to get taller 3 times taller. When we go to sketch this, again, I'm going to give you a couple of choices. What you can do is just right from the graph, you can see what the y value is and multiply that y value by 3. So here, the y value is 2. So this point, instead of being 2 units away from the y-axis, is going to be 2 times 3, which is 6 units away from the y-axis. This point here, which is 2 units below the y-axis, 2 times 3 would be -6 units below the y-axis. This point, that is 4 units above. 4 times 3 is 12. This is 1 unit below. -1 times 3 is -3, so 3 units below. This one, which is 3 units above, 3 times 3 is 9, so 9 units above. We can connect those dots. And there is our resulting graph. We can also do this, again, totally up to you. You might want to, instead of just moving the points on the graph, what you can do is get a table of values for the original function. So the original function would be the f at x. So -6, 2, -4, -2, 0, 4, 2, -1, and 8, 2. And then what you can do for g at x is just take those same coordinate points. It's a vertical stretch, so the x values are going to stay the same. The y values, though, are all going to get multiplied by 3. So 6, -6, 12, -3, and, oh, this one is 3, sorry. This is 3, so it's going to become 9 over here. And then you can just plot the points. Totally up to you. You don't have to do both. You can create a table of values. This would be 3y, or you can move them right on the graph. Okay, let's state the domain and the range for g at x. So the domain, the lowest x value, and does it state the, it doesn't. It doesn't matter what form we use. I'm going to just use interval notation here. So the domain for this one, the lowest x value is -6. And the highest x value is +8. The range, lowest y value is now -6. Highest y value is 12. Now, the number of invariant points. Well, we stretch this about the x-axis, so our x-intercepts are going to be invariant. How many x-intercepts do we have? We have 1, we have 2, we have 3, we have 4 invariant points. So this question is not asking us what the invariant points actually are, just how many there are. So this one has 4 invariant points. Let's move over and let's look at h at x. So h at x, we are given the equation for that. Let's just get rid of this. H at x is equal to f at 2x equals f at 2x. So our coefficient is in front of the x. It's not a parameter A. Here we are talking about parameter B. That means this is representing a horizontal stretch. Horizontal stretches for us are always going to be about the y-axis, and our stretch factor is going to be the reciprocal of the b value. So by a factor, not 2, a factor of 1/2. That means we are going to take all of the x values and multiply them by 1/2. When you go ahead and are sketching this, you can do it right on the graph, or you can create a new table of values and then draw the graph. It's up to you. So you might be able to see right away, oh, okay, this x value is -6. -6 times 1/2 is -3. So it moves in closer horizontally. -4 times 1/2, -2, 0. This is going to stay right on that y-axis. These ones are going to move closer. 2 units away, 2 times 1/2 is 1. 8 times 1/2 is 4. So that connect the dots and that squishes it right up. We can even really observe there that that is horizontally stretched by a factor of 1/2. If that confuses you a little bit, use your table of values from f at x, multiply all your x values by 1/2, and keep your y values. -6 times 1/2 is -3. -4 becomes -2. 0 stays at 0. 2 stays at 1. 8 becomes 4. Y values remain unchanged. Plot those points, and there is your transformed graph. Up to you how you want to graph it. You can just pull the points in or make a table of values and plot it. Our domain and range for h at x. Domain is lowest x value is -3. Highest x value is +4. So in interval notation, close bracket, -3, 4, close bracket. Our range, our lowest y value is -2. Our highest y value is 4. So our range, close bracket, -2, 4. And there is h at x. So really, really important that we look at the position of that coefficient. If it's in front, then it is a vertical stretch. If that coefficient is in with the x, it is a horizontal stretch. For the vertical stretch, our stretch factor is the a value. For the horizontal stretch, the stretch factor is the reciprocal of the b value. For h at x, we only had one invariant point because the invariant point was the y-intercept. Then we only have one of those, so we just have one invariant point. Again, it's not asking us for the value of the invariant point, just for how many we have, and there is just one invariant point for that one. Let's look at example 2. Given the function f at x equals x² - 8, write the simplified equation of the transformed function if A, it's stretched about the x-axis by a factor of 1/4, B, it's stretched about the y-axis by a factor of 3. Okay, so let's have a look at that. We are writing the equation. So because we're writing the equation, we need to pay close attention about where we're putting that stretch factor. Okay, let's read carefully. This is stretched about the x-axis. And again, I'm going to say this. We talked about this with the stretches. The x-axis could also be described as the line y is equal to 0. So just be aware, we can describe the x-axis in more than one way, either using the words x-axis or the line y is equal to 0. Okay, so when it's stretched about the x-axis, that means that this is a vertical stretch. If we are talking about a vertical stretch, that means we are talking about parameter A. We're talking about y equals A times f at x. Our stretch factor is 1/4. That means our A value is 1/4. So we're going to look at 1/4 times f at x. Well, what is f at x? F at x is up here. F at x is x squared minus 8. So our equation is going to be y equals 1/4 times x squared minus 8. Now again, those brackets are really important. If I just take the 1/4 and park it in front of the x squared minus 8 without using any brackets, I am not stretching the entire function. We want to stretch all of f at x. F at x here has two terms. That means that 1/4 is going to affect both terms. So be very, very careful when you're dealing with a function that has more than one term. When we put that A value in front, it's going to affect them both. We can distribute that 1/4 then, and it becomes 1/4 x squared. 8 times 1/4 is 2. And there would be our transformed equation. For part B, f at x is stretched about the y-axis. And again, I want to reiterate that the y-axis can be described as the line x is equal to 0. So be prepared to see either one of those. If we have a stretch about the line x equals 0 or about the y-axis, that means that we are dealing with a horizontal stretch. If we are dealing with a horizontal stretch, that means we are dealing with a, B value. Sorry. And the B value goes right in front of the x. So we are looking at y equals f at bx. Now, what is that B value going to be? Well, our stretch factor is 3, but be careful. When we have a horizontal stretch, this is the reciprocal of B. So if our stretch factor is 3, that means B is 1/3. So we're looking at f at 1/3 x. Well, what is f at x? F at x is x squared minus 8. So whenever we have a B value or f at bx, we are going to replace the x with bx. So instead of having x squared minus 8, we are going to have 1/3 x squared minus 8. So anytime we are using a B value, f at bx, we're going to replace x with the bx. We can just simplify this. We can square the 1/3 in the x. So 1/9x squared minus 8. And you'll notice that minus 8 is not affected. And that's because this is not an A value. A will get distributed to both terms, but B is just with the x. So we just replace the x with bx. There is your equation. Now, let's do what we did with stretches, and let's just graph all of those three so we can see what it is that we are talking about. So let's clear this out, and let's put those three things in there. So f at x, our original function, was x squared minus 8. X squared minus 8. Then we had our vertical stretch, 1/4 x squared minus 2. 1/4 x squared minus 2. And then we had our horizontal stretch by a factor of 3. So we had 1/9 x squared minus 8. So let's have a look at the graph and let's see if that makes sense. There's our original function. That's the one that should have been vertically stretched by a factor of 1/4. So it's been squished up by a factor of 1/4. All of these points got pulled closer to the y-axis, right? Here, look down here, -8. Quarter of that is 2. All of these got pulled down closer by a factor of 1/4, so that makes sense. Invariant points on the x-axis or x-intercepts. Whereas the black graph, horizontal stretch by a factor of 3. Sure that is. Look, it has been pulled right out by a factor of 3, where this used to be here at approximately 3, almost out here at 9. So, and invariant point on the y-intercept. So we can see that the equations we've written are correct because they show the transformations that are described. Your job now, go ahead and try these homework questions and then see your teacher if you have any questions.